Okay, so in this video, we'll continue to talk about sequences, and we'll go into more detail about limits of these sequences. Consider the sequence, for instance, a sub n is equal to n over n plus 1 plus 2 raised to negative n. Okay, so, I mean, you could just start plugging in numbers and see what happens here, right? A sub 1 is equal to 1/2 plus 1/2, that's equal to 1. A sub 2 is 2/3 plus, what is that? That's 1 over 4, and that's 11 over 12. A sub 3, and well, I mean, you get the picture, right? We can keep going forever here. And we're not necessarily going to have an idea of what the limit of the sequence is going to be like. Now, okay, let me just compute this because I'm getting annoyed here. This is 7 over 8. Okay, I just wanted to get that out of the way there. But what we really want to know here is, well, what happens as n goes to infinity? Right? Do we even know if this is convergent or divergent? Now, remember from the previous examples we did that the limit as n goes to infinity of n over n plus 1, we said that, hey, that looks like it's getting closer and closer to 1 as n grows larger and larger. Right? So remember the intuitive definition. The limit is said to be 1 if we can make these terms, n over n plus 1, close enough to 1 as we would like, by taking n large enough. Right? And I'm not going to go over like the precise definition here that you'll see in some textbooks, right? But intuitively, that's what it means. How about 2 to the minus n? What do you think happens to 2 to the minus n as n goes to infinity? Well, we kind of know what happens to the graph of y equals 2 to the minus x, right? It has a horizontal asymptote at y equals 0. Right? As x goes to infinity, well, that's just 1 over 2 to the x, which goes to 0. And so we're going to make a guess here that, hey, maybe the limit of 2 to the minus n is 0. And maybe if we define our sequence to be the sum of these two terms here, then its limit is going to be 1 plus 0, which is equal to 1. Right? And that seems like an ad hoc method for now. And again, that's because we're not really going into this precise definition of what the limit actually is. But it turns out it's quite reasonable to do this. And, well, let's go through a number of limit laws, actually, that help us compute these limits and help give us a framework of talking about these limits. First thing I want to mention is this idea I have down here, that somehow knowing what the function does helps us determine what the sequence does, right? So we're talking about two different things here. Function in the real numbers and a sequence where your inputs are natural numbers. And that's the content here of this next theorem, right? It actually relates the limit of a function to the limit of a sequence if you know that that sequence is actually matching with the function values at all the natural numbers. Right? So the theorem says, if you have a function f of x, you take x, let it go to infinity, the limit is L. Right? So in our previous example, y equals 2 to the minus x approaches 0 as x goes to infinity. Well, if we define a sequence such that it matches with a function on all the natural numbers, okay, so what does that mean? Remember that to graph the sequence, it's just basically plotting points, right? Where you're plotting them at n equals 1, n equals 2, n equals 3, and so on. Right, so that's 1/2. That's 1 over 4. And clearly this is not drawn to scale, but you'll get the idea. That's 1 over 16. So this theorem says if your points are on the function right? If all the points of your sequence are on the graph of the function f, then the sequence, as n goes to infinity, has nowhere else to go but L as well, but the same limit. Again, look at the picture, it just makes sense. The red dots have to follow wherever the blue curve goes. And if the blue curve has limit 0, then the red dots has to have limit 0 as well. Okay, and that's actually a very nice theorem, right? Because now, whenever we have a sub n given as a formula, we can just apply this theorem and say, well, I know the limit of n over n plus 1 is 1 because of this theorem, and the fact that as x approaches infinity, the limit of x over x plus 1 is equal to 1. Now, aside from this, there are, well, all these other laws. I'm not going to go through all of them. A lot of these you will have seen before in differential calculus, actually, when you're computing limits of functions. For instance, the limit of a sum is equal to the sum of the individual limits, as long as the individual limits exist. Same thing for the difference. Scalar multiplication, you can bring the c outside, and reasonable things like that. You have a quotient here, you have a power rule. You even have a squeeze theorem for sequences. Aha, that sounds interesting, right? But the idea is the same as with functions. If you have a sequence a sub n, and you have a sequence b sub n, such that the sequence c sub n, so let me start with the natural numbers here, only on this side. Right, so if you have two functions here, two sequences an and bn, and the sequence cn is somewhere inside or in the middle of them, then cn, if a and bn have the same limit, then cn has to also be squeezed in the middle of a and bn and get the same limit. And you can actually use this to prove the next one. If the absolute value of an has limit 0, then an has limit 0. And the last property here talks about, well, what if you apply a function to a sequence? Well, as long as the function is continuous at your limit, then the limit of the new sequence is going to be the function evaluated at the old limit. Again, some reasonable things that we would expect to be true. So here's another example. What's the sequence ln of n over n? Is it convergent or divergent? If it's convergent, determine the limit. And here, we're going to look at the function. Right, again, if we know where the function goes, then we know where the sequence goes. To take the limit as x goes to infinity of the function ln x over x. Okay, so that's infinity over infinity. So you apply L'Hopital's rule, take the derivative 1 over x over 1, and this is now 0. Therefore, the limit as n goes to infinity of ln n over n also goes to 0. By that same theorem that we talked about before. And let's end this video with one last example here. A general example that will actually help us in some of the other things we'll be doing in this chapter. It asks, for what values of r does the sequence r raised to n converge? Right, so you don't have a number here for r. In fact, it's asking us, do we know exactly? If I plug in, say, r equals 2 and get 2 to the n as my sequence, does it converge or not? If I plug in r equals 0.1, does it converge or not? Can I characterize the set of real numbers r for which this converges? It turns out we can, again using that same theorem as a while ago. Right? Knowing where the function goes helps us determine where the sequence goes, right? As long as the sequence formula matches the function. Okay, well, let's actually work on the more easy cases here for r. Right? In fact, if r equals 0, we know what the sequence is going to look like, right? This is just a sequence of zeros. And this has limit 0. Okay, so that was pretty trivial there. Same thing for 1. If r equals 1, we get 1, 1, 1. So just a bunch of 1s. This has limit 1. So far we found 2 values of r for which the sequence converges. For an obvious example where it diverges, take -1. We also saw this before. This is -1 to the first power, so we start with a -1, then 1, and so on. Okay, so let's characterize the other values of r. Right, so if you were to visualize on the number line what we've been doing, at 0 and at 1, it converges. At -1, it's divergent. So we have all these other real numbers to check. Okay, so the easier thing here is to look at the case where r is positive. Okay, if r is positive and larger than 1, so somewhere here to the right of 1, what do you think is going to happen? Well, the graph of y equals r to the x looks like this. Right? From your lessons on the exponential functions, if your base is larger than 1, right, r to the x, well, it blows up. It goes to infinity as x goes to infinity. Therefore, the sequence will also blow up to infinity. So it's divergent. So it's divergent here. Okay, what's next? What if r were in between 0 and 1? Again, from your lessons on the exponential function, what is the graph of y equals r to the x? Well, it's going to be this graph, but looking something like this instead. Let me draw that nicer here. There. All right, and in this case, again, your sequence, since they match the function formula, they're just going to follow the function where the function goes. So limit n goes to infinity if r to the n in this case is 0. And it converges. Okay, how about the negatives? Well, if r is less than -1, well, can we even draw the graph there of r to the x? Right, we can't, right? But what happens to the sequence? Well, we're only taking powers to be natural numbers there. So what's going to happen is you're actually going to get a similar sequence as when r is larger than 1. But since you have a negative raised to n as well, the signs are just going to alternate. Right? In fact, I can write it this way. If you get something like -5 to the n, let's pick r to be -5, then you can write this as -1 to the n times 5 to the n. And so the sequence there is going to be -5 and then 5 squared and then -5 cubed and so on. And what that's going to look like on our graph is that the points of your sequence are actually going to alternate from negative to positive, negative to positive, but following either one of these branches. Therefore, the sequence there is divergent. Right? It was divergent even for a positive base. since it blew up to infinity. Now it's blowing up to infinity, but also alternating in sign, right? So it's even more divergent. That's not a thing, but it's divergent. Okay, so I'm just going to put some x's here. Lastly, what if r is in between -1 and 0? It's going to display the same behavior as what we did here for -5. Can't draw properly. Okay. It's going to alternate in between the graphs of, in fact, I can write it this way, right? Negative absolute value of r to the x and absolute value of r to the x. And your points are still going to alternate because you have r negative, but in this case, it's actually going to 0. So it is convergent here. Right, so that's pretty interesting. In fact, we can't actually use that theorem on functions to prove this result here, that it goes to 0. Right? Because again, it doesn't make sense to just say -r to the x. Right? But you can see what happens here on the graph. And in fact, we'll try to think about that. How do you actually prove that r raised to n goes to 0 if r is in between -1 and 0? Right, I'll give you a hint. You can use one of the laws in that huge page full of bullet points that you saw previously. And you'll be able to prove that the limit is 0. Right, so let me just summarize here. Therefore, the sequence converges for r -1 to 1, 1 inclusive.